Engineering application. The most important application of the concepts of availability and exergy is to analyze a single device and complete system with respect to energy transfer. The most important application of the concept and exergy is to analyze single devices and complete systems with respect to the energy transfer as well as the exergy transfer and destruction. As well as the exergy transfer destruction. Consideration of the energy terms leads to the first law efficiency as a conversion efficiency for heat engine or a device efficiency mean, measuring the actual device relating to the corresponding reversible device. Focusing on the exergy instead of the energy leads to the second law efficiency for devices as shown in equations 31 to 34, which was, for example, eta for second law turbine, which was W actual on the for pump second law we have heat exchanger, or we have the P source available energy minus irreversibility on P dot source. The formulations are also available in the previous chapter. These second law efficiencies are generally larger than the first law efficiency. Eta the second law greater than eta first law, as they express the operation of the actual device relative to what is theoretically possible with the same inlet and exit state and the actual device. This is different from the first law efficiency, where the ideal device was used in the comparison does not have the same exit or end state as the actual device. These efficiencies are used as guidelines for the evaluation of actual devices and such systems, pumps, compressors, turbines, and nozzles, to mention a few common devices. Such comparisons rely on experience with respect to the judgment of their results. Is a second law efficiency of 85% considered good enough? This may be excellent for a compressor generating a very high pressure, but not good enough for one that creates a moderately higher pressure, and it is too low for a nozzle to be considered good. Besides using a second law efficiency for a device, as previously shown, we can use it for complete cycle systems such as heat engine or heat pumps. Consider a single heat engine that gives out actual work from a high temperature heat transfer. Consider a simple heat engine that gives out actual work from a high temperature heat transfer with the first law efficiency. So with a simple heat engine, the first law efficiency says that W of heat pump equals to eta heat pump Q1 to H. What then is the second law efficiency? We basically from the same relation but express it in terms of exergy rather than energy, and recall that work is 100% energy. For the second law, use exergy relation. The heat pump equals to multiply to phi H. Which is equals to eta heat pump T on T0, the availability term related to heat transfer. A second law efficiency for a heat pump would be the ratio of exergy gained is for heat engine, and for heat pump we have a second law. We have COP for heat pump, which was Q H, for example, on W heat pump. In the first law, and for the second law, we have also beta of heat pump. In this case, we don't use Q, we use phi, available term related to the on the heat pump work. Availability related to heat transfer. A similar but slightly different measure of performance is look at the exergy destruction terms, either absolute or relative to exergy input from the source. Consider a more complex system such as a complete steam power plant with several devices. If we do the analysis of every component and find the exergy destruction in all parts of the system, we would then use those findings to guide us in deciding where we should spend engineering effort to improve the system. Look at the system parts that have the largest exergy destruction first and try to reduce that by altering the system design and operating system. For a system of devices, let's first look at the device with largest energy distribution. Largest exergy distraction and try to decrease destruction with change the system properties. For the power plant, for instance, try to lower the temperature difference in the heat exchanger, reduce the pressure and heat loss in the piping, and ensure that the turbine is operating in its optimal range. To mention just a few of more important places that have exergy destruction in the steam condenser, a large amount of energy is rejected the surrounding, but very little exergy is destroyed or lost. So the consideration of energy is misleading. The flows and fluxes of exergy provide a much better impression of importance for the overall performance.